Hello, let's learn theorem of geometric mean. Prove that in a right angled triangle the perpendicular segment drawn on hypotenuse from opposite vertex is the geometric mean of the segments into which hypotenuse is divided. Okay, as per this situation we need to draw a diagram of a right angle triangle, and in a right angle triangle we are interested to draw perpendicular on hypotenuse through opposite vertex, means through vertex of a right angle. Okay, let us suppose triangle PQR is a right angle triangle at vertex Q, and seg QS is perpendicular to hypotenuse PR. This is situational diagram. Okay, antecedent part of this statement tells us in a right angle triangle the perpendicular segment drawn on a hypotenuse from the opposite vertex. Okay, this is antecedent part, and antecedent part we used to write as given. Let's mention what is given. Given in triangle PQR, angle PQR equals 90 degree, means triangle PQR is a right angled triangle. Okay, now in this triangle seg QS is perpendicular to hypotenuse PR such that P dash S dash R. Then its consequent part is that segment is the geometric mean of the segments into which hypotenuse is divided. Means seg QS is the geometric mean of seg PS and SR, because seg QS divides hypotenuse PR in two parts, PS and SR, and we know that geometric mean is a term among three terms such that square of the geometric mean equals product of rest of two terms. Means in this case QS square equals PS into SR, that we have to prove because it is consequent part in a statement. To prove, what to prove? QS square equals PS into SR. Okay, that is QS is equals under root PS into SR. Okay, now information is sufficient. Let's start the proof. In a triangle PQR, angle PQR equals 90 degree. Seg QS perpendicular to hypo PR, P dash S dash R. All these things are given. That's why we are going to give logical reason since given. But we learned that in a right angle triangle, perpendicular drawn through the vertex of right angle on a hypotenuse divides that triangle in two triangles, which are again right angle triangles, and they are similar with original triangle and with each other, and that we call as similarity of right triangles or similarity in right angled triangles. Okay, and as per that similarity of right triangles, triangle PQR similar triangle PSQ similar triangle QSR as per the correspondence between their vertices. Let's mention here. Therefore, triangle PQR similar triangle PSQ is similar with triangle QSR. Since similarity of right triangles or right angled triangles. Okay, similarity of right angled triangles. Now we are going to select a pair of triangles such that who will give us QS, PS, ESR, because we are interested to prove QS square equals PS into ESR. If we consider triangle PQR, it does not contain QS, PS, ESR. Okay, let's consider triangle PSQ and QSR. Yes, triangle PSQ, which contains PS as well as QS. And what's about triangle QSR? It contains QS and ESR also. Means we are going to select second and third triangle. Means these are daughter triangles we are going to consider. Therefore, triangle PSQ similar triangle QSR. And now we are going to consider CST, corresponding sides of similar triangles. Okay, out of 3 pairs, we are going to consider only 2 pairs, which will give us QS square equals PS into SR on cross multiplication. Before that, we need to write the ratio. Okay, ratio of corresponding sides of similar triangles. Okay, QS of first triangle correspond with RS of second triangle, and again, as we are interested with QS of second triangle, which will be at the denominator, PS correspond to that QS. Means here we need to write PS upon QS. QS upon RS equals PS upon QS, since corresponding sides of similar triangles. And therefore, now by cross multiplication, QS into QS gives us QS square equals PS into RS. PS into RS, that is QS square equals PS into SR. Okay, and therefore by taking square roots of both sides, we get QS equals under root PS into SR. Hence the proof. Thank you.